In this video, I'm going to use Wolfram-Cloud, Mathematica, and play around a little bit with dice, rolling dice, and distributions, and so on. But it's not going to be a simulation. It's going to be going to find sort of the distribution of, and here are my definitions. I'm going to have an NS sided die. So I'm going to have, instead of just always having six, I'm going to have NS as the number of sides of the die. So effectively, if that's two, it's more like it's a coin. And then ND is going to be the number of such dice that I roll in a given roll. So I might roll three six-sided dice, ND, NS sided dice. Okay. And so I make this sort of generating function dice that depends on NS and D and X. I'll sort of put it in and then I'll sort of expand it and sort of show how that makes sense. Shift enter. Okay. And then I'm going to take for 6 and 1 for a six-sided die with just one of them. I'm going to take that function, a series of that function around x of 0 and get six values. And there are only, for that, for ND of 1, there are only six values. But I didn't want the Mathematica will sort of carry around the plus x of order 7, and the normal gets rid of that. So dice is my function that I defined above. Series will take a series expansion of it. And then this word normal out front will get rid of any of the, the series always has that sort of telling you how far you went plus order x seventh, and I wanted to get rid of that, and normal does that for me. So here is this sort of generating function for one six-sided die. It's x plus x squared plus x cubed up to x to the sixth, and then you can sort of see where this sort of came from. Sort of well known that that's sort of geometric, starting at x rather than starting at 1, and it's a finite. It stops, it truncates, but the sort of same trick you can use to solve a geometric series, you can use to solve this. So summing that, you would sort of get x times 1 minus x to the sixth divided by 1 minus x in the denominator. And then I'm taking this guy and sort of raising the whole thing to ND, which is the number of dice. So I'm sort of taking the result for one die, which is sort of saying the coefficients are related to the number of times something happens, or maybe the probability of something, but here we'll just say the number of ways or something. So there's, if I'm rolling one six-sided die, there's one way to get a 1, one way to get a 2, one way to get a 3. That's what these coefficients mean. Now, if I take the same game, but I'm going to stick with a six-sided die for now, but I'm going to have 3 of them. So I'm going to make ND 3, and I'm going to expand it. Goes up to 18. I could just make this series sort of a large number because it really does stop at 18. And then the normal would throw away any sort of extra stuff. But there it is. And so what this can do for you is determine for you, and there are other ways of doing it, but this sort of function generates for you, tells you sort of how many ways. So if I'm rolling 3 six-sided die, how many ways are there to get a 3? Well, there's 1. How many ways are there to get a 4? There are 3. How many ways are there to get a 6? There's 10. So I decided to show them. So here is, if the first die were a 1, Then the second die could be a 1, and the third die a 4. So 1, 4, 2, 3, 3, 2, 4, 1. If the first die is a 2, there's 1, 3, 2, 2, and 3, 1. And then if the if the first die is a 3, there's 1, 2, and 2, 1. And if the first die is a 4, then it's 1, 1. So those are all the possibilities, and there are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. And so that's what this sort of generic function can do for you. I'm putting in a specific NS and ND here for a moment, and then I'll sort of generate a bunch of them. But now I want to sort of generate sort of, I don't know, a sort of perfect series of die rolls. So I want, I don't want to do some simulation with a large number, but I want to do, I want to roll the dice. What did I just say? I'm rolling a 6-sided dice twice. So I want, there was one way to roll a 2, both ones. There were 2 ways to roll a 3. So I want them both sort of represented. So I'm making a distribution where every number appears the number of times and it is possible to get on the dice. So how am I doing that? So I'm taking what I had above, the dice, the series, the normal, and I'm going up to NS times D. And so that generated, that is just sort of this for my choice of NS and ND. So that is that sort of generating function. Okay. Now I am, and I start off with something I'm calling this distribution I'm going to make, and it starts off empty. And then I have a loop over the terms. So the lowest term is ND, X, sort of X to the ND, all ones. And then the highest term is X to the NS times ND. If all the dice, if all ND dice ended up on the highest side, that would be my highest power. Okay, so if it's 3 6-sided dice, I'm going to go from 3 to 18. So this is my for loop in Mathematica language. It's a method, and so the parts are separated by commas, and the where I'm initializing the condition under which I continue my incrementing, and you just type when you're typing into Wolfram-Cloud. If you type the less than followed by an equals, it sort of turns it into this symbol. Okay. And same sort of for the plus plus. If I hit 2 pluses in a row, it sort of changes it to a plus plus symbol. Okay, so I have a loop over all of my possible powers, and then I'm making a function that just sort of counts, goes from 1 up to the series coefficient, grabs the as it says, the coefficient of my series. So my gen was a series. I'm pulling out a series coefficient, and I'm saying that the variable is x. It's expanded around 0, and I'm getting the ith one. So that was sort of 4, as we saw over here, like when I is 6, it's going to give me 10. So I'm going to be in this inner loop 10 times. And then I'm adding that 6 to my distribution 10 times. So 1, 2. But this wasn't 3. Let me do the 3 because I'm talking about it. So that would make more sense. So here's 3 6-sided die. And then let's do this And so then I'm making the 6 can occur in 10 ways. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 sixes in there to say that there are the 6 ways. So there's one way for a 3, one way for an 18, 3 ways for a 4. So that's the game. Okay. So that is this distribution. Then I can do some normal statistics on my distribution. I can get the mean. I can get the variance. I can get the kurtosis. The skewness is just going to be 0. These are sort of even about the mean. So it's nothing interesting there. Okay. Now what I do, so um, I'm starting off for a given sided dice. So I'm doing for a 6-sided dice. And then I'm going to sum over various numbers of dice. So ND is the number of dice and S is the number of sides on each die. And then I'm going to get a set of statistical results. So that's what results is, an empty list. And then I'm going to get statistical results in there. And then, so I'm just doing what I did above, but over and over again. Okay. So I'm going to get my sort of generating function. And so this is just the repetition from here to here. This is generating that, getting that generating function. Using the generating function to get the distribution. So we're generating this distribution. So that's sort of perfect representation of what can happen when I'm rolling ND dice with NS sides. Okay. So I'm making the distribution, and then I'm gathering the statistics on that. So I'm making a tuple, and I'm just going to add some statistical properties. So I'm going to add the ND, how many dice there were. I'm going to grab the mean of the distribution. I'm going to grab its variance, and then I'm going to play with the kurtosis. Now I want to sort of for a normal distribution, the kurtosis goes to 3. And so people will often talk about the excess kurtosis, sort of have something that heads toward 0 for as something becomes more normal. And so we think that as we add dice, the distribution of dice sort of tends towards a normal distribution. And so people usually take the kurtosis and subtract 3. I'm going to turn that around because I was getting negative numbers and I wanted positive numbers because I want to plot it and fit it to a power. So that was easier for me if it was positive. So I'm going to say 3 minus my kurtosis. And I called it, like, I don't know, the deficit or the deficient kurtosis instead of the excess kurtosis. But I just wanted to point that out. Okay. So I'm doing 3 minus the kurtosis. Again, they usually subtract 3. Kurtosis minus 3. I'm doing 3 minus kurtosis just because I wanted positive numbers and for no better reason than that. So I'm using my generating function to sort of generate this representative distribution. And then I'm getting the statistics for the distribution, the number of dice itself, the mean of the distribution, the variance of the distribution, and this, I'll call it the deficit kurtosis. And then I am collecting those results. So for here, I have a 6-sided die, and then I'm going to have 1, 2, 3, 4, 5, 6 dice of that type. So then I can I'll run that. Takes a little while. Uh, as the sides of the dice get bigger, it takes longer. And so when I was playing around, when I got sort of, if I wanted to look at a nine-sided die, then I couldn't go up to as many as six of those dice because I was running out of what Wolfram-Cloud would do for me, sort of for free. You go with the free version. Okay. So here are the results. So this was a six-sided die the for one roll of the die, the average, the mean was 7/2. The variance was 7/2, and the uh, kurtosis was this 222 on 175. Okay. I wanted to show how to, from my results, I wanted to extract just I called it the the kurtosis is the deficit kurtosis, kurtosi, I don't know. All right, so I'm taking my results, which is a list of lists, but I only wanted to plot. So I'm taking all of so this is sort of representing if you will, the rows or that I want, starting at 1 and going and doing this semicolon, semicolon -1 means I sort of want all of these terms. And then this curly bracket 1, 4 means I want how many dice were there. These were all six-sided dice. But how many dice were there? And then for what was the kurtosis? So that's just a sort of a selection game here. And then I am plotting that. And again, this was my weird choice of the kurtosis, was that I wanted it to tend towards 0 to emphasize that it was becoming normal, but I also wanted it to be positive because I'm going to fit it to a power law. So there is my list plot of these kurtosis values. And then I'm going to fit that to a power. So I have this power law behavior, a times x raised to the b. I'm going to use a and b as fitting parameters, x as a variable, and I'm going to fit that. Okay. And I did not plot that. We'll see in the end that that's quite accurate, because I went and did. So then I just pretty much have the same thing again. And I was just varying S, varying D, collecting results. So now I'm on NS equal 4. Just happens to be where I ended. I was up and down all over the place, but just in the history of things, that's where I ended up. And it also comes out pretty quickly. Again, if the sides of the dice gets large, then I have to sort of cut back a little bit on my ND. Okay. And then I just sort of stared at these numbers for a while and found that a formula for the variance in terms of NS and ND. Now, in the variance, you know that you divide by the number of samples minus 1. So my number of samples is the number of sides raised to the number of dice. And then, so that's the number of samples, but then in this sort of I'm not doing random samples, I'm doing sort of a perfect set of samples, but that is the number of samples in S raised to the ND. And then in the variance, you end up dividing by the number of samples minus one. So that's not, that denominator there is not unexpected. Okay. And then I sort of, so knowing that from that clue, I could start to pick out the rest of the behavior. And it seemed to be ND, the number of dice, times the number of sides raised to the ND minus one, times N, the number of sides cubed minus the number of sides, and that was all divided by 12, and that number of samples minus one. And so here is, let me enter that function. And then here was for 6 four-sided dice. There is the 204 on K. And let's try 4 four-sided die. There is the 256 over 51. And let's just change the number of die sides to 5 and run it again. And this turns black, and then when it's no longer black, we have an answer. And what do we have now? A 5-sided dice. So, and we had 4 5-sided dice. Where are we at? I changed the wrong number. We have 4 5-sided dice. I'm confusing my NS and ND. And there is the 625 over 78. And then I looked for the kurtosis, but I'm doing this deficit kurtosis thing. And I found this formula. So it's a bit simpler looking. In the sort of kurtosis game, that sort of ugly denominator of the number of samples minus one sort of, I don't know, more or less cancels out, and you sort of the numbers aren't quite as crazy in the kurtosis than they are in the variance, even though you think like a higher moment would be more complicated. But because it's sort of scaled by the variance, it sort of takes some of that out. Okay, so it was, here is the formula I found. It just goes simply as ND. Everything else is NS. So up here, this was for a 6-sided die. So let's change this to a 6-sided die. Oops, sorry. And let's get all the values for a 6-sided die. And solid black, and then when this is no longer solid, then I have my answers. There we go. And let's just try this for a 6-sided die. So this is back to the variance for the 4 of the 6-sided die. There's the 432 over 37. And this was the formula. Let's enter it for this deficit kurtosis, and let's do it for 5 6-sided dice. 222 over 87. There it is. Let's do 4 6-sided die. 1 over 350. Okay. And then let's do, and then the formula here for this kurtosis thing, the only place ND appears is as a single power in the denominator. So if I know the value for uh, one one dice, so this is one six-sided die. If I know the kurtosis, then I know that from then on, it's just that on ND. So let me take numerically what that is. And I have this 1.26875. It was this, this crazy number 222 on 175. But if I take that up to here, this was my fit, and it was 1.26857. So it was the fit, and I didn't put the fit. You showed put the fit and the data together, but it would have been a perfect fit because the behavior on ND is just a power of -1, and this was the coefficient which it had. All right, that's what I want to show you, just some playing around with mathematical Wolfram-Cloud, and dice distributions got as a function of the number of dice and the number of sides of the dice, some generic results on the variance and the kurtosis, sort of the second moments and fourth moments. All right, that's all I wanted to show you on this one. Thanks for your attention.